So this is going to be the homework for the salts part of the unit here. Sorry, give me a second. So we're going to be looking at Ka, Kb values and their relation to their conjugate Kb, Ka values. So using the Ka values in Appendix E to list conjugate bases following acids in order of increasing base strengths: formic acid, hydrofluoric acid, benzoic acid, and phenol. So we're going to first look at the Ka values of all these things, and I believe they are given in, let's see, so Ka of formic acid equals 1.8 times 10 to the power negative 4 of hydrofluoric acid is 6.3 times 10 to the power negative 4, so slightly higher Ka. Benzoic acid, that is 6.3 times 10 to the power negative 5. Interesting. And phenol is, I can't even find phenol. Oh, it's right up there. 1 times 10 to the power of negative 10. Okay, so one option is to actually calculate the Kb of the conjugates, right? And we can do that. I should have zoomed in. So I'm going to zoom in here so that I can write bigger. Kb of conjugate. So Kb of methanoate, again, do 1 times 10 to the power negative 14 divided by this Ka. So 1 times 10 to the power negative 14 divided by 1.8 times 10 to the power negative 4, which gives me 5.5 times 10 to the power of negative 11. F minus, again, 1 times 10 to the power negative 14 divided by 6.3 times 10 to the power negative 4 is 1.58 times 10 to the power of negative 11. Benzoic acid, so benzoate, O8 is, I do the same calculation, I get 1.58 times 10 to the power of negative 10. I think, unless I'm going crazy. Yep, no, that's correct. And phenoate is going to be 1 times 10 to the power of negative 4. So here, if we look at our acids, again, the Ka gives us the extent of reaction, so how much H3O plus is produced for each of these acids. We'll rank them in order. So this is going to be our strongest acid, our strongest weak acid, so to speak. It's not a strong acid, but it will be our, it's the strongest weak acid. This will be second, this will be third, and this will be fourth, just because I'm just ordering them in order of increasing Ka values. So decreasing Ka value, because the highest Ka value, which is HF, will be our strongest acid. Then we have this, this, and then this. And we can see here from our Kb values that the order is reversed. This has, phenoate has the highest Kb, and so it will be the strongest conjugate base because its acid is the weakest of the four. Right, so the weak acid will have the strongest conjugate base, and we'll basically have to reverse orders of 4. This will be 2 because this is the next lowest. Then this will be the next lowest, and F minus because its conjugate acid, or its acid that it came from, is the strongest acid. It will have the weakest conjugate base. Right, so just looking at that. That chart that we that's later on in the textbook, we'll go over there briefly after we complete a couple more questions. But the stronger the acid, the weaker the conjugate. So because all of these are technically weak acids, by definition they're weak acids, their conjugates will also be weak, but relative strength is what we are comparing here. So Kb for ammonia 36 is that. Kb for triethylamine. Which is the stronger acid, NH4 or that? Okay, so again, we'll just look at the values here. So we're not going to do the actual calculations, but here we can see that Kb for trimethylamine is higher. So Kb for trimethylamine is greater than Kb for ammonia. And so the opposite is true. So the Ka for trimethylammonium, I don't even know what that is. The Ka for this guy, CH3 thrice NH plus, will be greater, or whoops, will be lesser than the Ka for ammonia. Trimethylamine is a stronger base, so the conjugate will be a weaker acid, just like we had over here. A stronger acid gave a weaker conjugate base. The weak acid gave a strong conjugate base. Same as reverse, right? Strong base gives a weaker conjugate acid. A weaker base, relatively, gives a stronger conjugate acid. So NH4 plus here will be the stronger conjugate acid. All right, so sodium benzoate, calculate pH of 1 mole aqueous solution of sodium benzoate. Okay. So 37. We have to do our ice table, and again, we're going to ignore the sodium bit because Na plus is not going to react with water. We talked about this in our previous video and in class. Na plus is the conjugate acid of a super strong base, sodium hydroxide, and therefore it is a super weak acid, and therefore will not react with water in any measurable or anything of importance. It will not react. So we're only going to look at the benzoate part, and we'll draw our ice table. So benzoic acid. Oh, I have space here. Benzoic acid plus water. Oh, whoops, benzoate ions comes first. Benzoate plus water gives benzoic acid plus OH minus, right? Because benzoate is C6H5COO minus plus water gives H5COOH plus OH minus. That's the reaction, and I have just 1 mole per liter of this. I can ignore my water. 0 minus X plus X plus X 1 minus X. And this is very similar calculation to calculating, the pH of a weak acid that we did, just Ka, Kb calculations. The only difference here is when we have our Kb of benzoic acid, we cannot just get that from a table. We have to do 1 times 10 to the power negative 14 divided by Ka of benzoic acid, right? And this can be got from a table, and you always have to do this little extra calculation when you are doing a pH of a salt. So 1 times 10 to the power negative 14 benzoic acid. I think we already found that above, but we'll do it again. 6.3 times 10 to the power negative 5. Is equal to 1.587 times 10 to the power negative 10. So now I can do my small x approximation. 1 divided by Kb greater than 500, therefore justified, get this out of the way, and I have, KB is 1.587 times 10 to the power negative 10 equals x squared divided by 1. The minus x is gone. It's products divided by reactants. So the x is just take the square root of that. 1.26 times 10 to the power negative 5. And therefore, where was I? That x is OH minus concentration, right? So I take the negative log of that. I obtain 4.89 for my POH. And therefore my pH can be calculated by doing 14 minus this, which is 9.1. Chemical equations to show how it acts as an acid and a base. So HSO3 minus plus water. So let's do it acting as an acid first. So it's going to get rid of that H. So leaves me with SO3, 2 minus plus H3O plus. Next, let's do it acting as a base, where that is going to accept a proton from water, which is going to be H2SO3 plus OH minus. There we go. Because this is gone over here, the OH minus stays in lieu of the water. So that was our homework for this. I think we will continue to do, because this was page 409. So we're going to continue with the homework, I think. So this was the chart I was talking about before, the strong acid. So look at this chart, very important, or very useful, I should say. We're going to continue with this little chart over here. Okay, so now we will look at we will look at each salt and predict whether it's acidic, basic, or neutral. Okay. NaCN comes from NaOH and HCN. This is a strong base, weak acid, therefore basic salt. That's one way to do it. The other way to do it is to say NaCN splits into Na plus and CN minus. Na plus gives you no reaction because it comes from NaOH. CN does give you a reaction. It acts as a weak base in water to give you HCN and OH minus, which means that OH minus is produced, which means it's basic. Similar ideas, but same solution. Magnesium nitrate comes from magnesium hydroxide and nitric acid, both of which are strong, so that's a neutral. Lithium fluoride comes from lithium hydroxide plus HF, which is again a strong base, weak acid combination, which means this is going to be basic. Because again, you can split that into lithium and fluoride ions. This is going to give you no reaction. This is going to react with water to give you a little bit of OH minus ions, so which makes it basic. NH4I can be split into, again, it comes from ammonia and hydroiodic acid, which is a strong acid, weak base combo, so we know that's acidic. And we can also split NH4I into NH4 plus and I minus, which I minus does not react with water because it's a conjugate base of a strong acid. This does react with water to give me ammonia plus H3O plus, which contributes to the acidic character of the salt. Okay, NH4BrO4, strong acid, weak base, acidic. NaBrO4, strong acid part, strong base part, so that's neutral. Right, because this was HBrO4 and NaOH. This was NH3 and HbRO4. So you can split these into the ions NH4 plus, BrO4 minus. This is not going to react, it's strong. This is going to react. NaOBr, strong base. Bromate is a weak acid, and therefore this is going to be basic. NH4Br is going to be also acidic because you have an HBr, which is a strong acid, and NH3, which is a weak base. So strong acid, weak base combination gives you acidic. Ka for benzoic acid is 6.3 times 10 to the power negative 5. Ka for phenol is that guy, which is a stronger base. This is very similar to the one that we just did. So I know that benzoic acid is a stronger acid because it has a higher Ka. So we'll say benzoic acid is stronger because it has a high Ka, or higher Ka, I should say. It's not a strong acid, it's just stronger than phenol. And therefore, benzoate is weaker conjugate base, right? Because it will have a lower Kb if you do the calculations. And so which is a stronger base? It will be actually phenoate, or phenoate ion will be the stronger one, which is the conjugate base of phenol. Because phenol is the weaker acid, it will have a stronger conjugate base. It's very important to understand this dichotomy. Okay, so NaHSO3. This can act as an acid to give me well, the Na plus is inconsequential, so I'm just going to ignore that, right? It's just the HSO3. It can act as an acid to give me SO3 2 minus plus H3O plus. And the Ka value for this is, in fact, do I have an HSO3? 6.3 times 10 to the negative 8. You won't be asked this question because it's technically in the polyprotic acids kind of deal, but it's not really too hard. This can also act as a base to give me H2SO3 plus OH minus. And here I have to do the reverse calculation because I'm given Ka of this acid in my chart, which is 1.4 times 10 to the negative 2. So my Kb of the conjugate is divided. That's okay, 7.14 times 10 to the negative 13. And I got this value. This acts as a base, so I have to do Kb there. Whoops. I got this value because Ka of H2SO3 was given to me as 1.4 times 10 to the power of negative 2. Right, and using that I can do 1 times 10 to the negative 14 divided by 1.4 times 10 to the negative 2, which gives me my Kb value. Right, so I did Kw divided by Ka gives me my Kb, and I can see here that HSO3 is going to act as an acid much quicker than it's going to act as a base. So it almost never acts as a base. It always will act as an acid in solution because the Ka for the acidic reaction is greater than the Kb for the basic reaction. So acid, it's going to be acidic solution. And we're going to do titrations in another video because those are bigger calculations. So I will sign off on this one. See everybody in class.